second speaker of the session. We're happy to have Jiji on. Some comments on axion dark matter.
Yeah, thanks. So actually, this will be the first more particle physics-oriented talk. So I was asked to give a review on axion dark matter and dark photon dark matter, but I couldn't do it even allow myself 30 minutes. So I just make actually 3 comments on axion dark matter, its observables, and the related simulations. And I also should say ahead of time, just these comments are not really new comments. They are known like in the literature, but I think they're important points that are worth emphasizing to a broad audience. So let me start with a very quick review of what axion is. Okay, so axion is a periodic pseudoscalar, compact pseudoscalar field. So it lives on a circle. So when you shift this axion by integers times 2 pi fa, where this fa here is the axion decay constant, or in terms of a dimensionless variable, the theta, which is a ratio of a over fa by integers times 2 pi, the physics should remain invariant. So it could be in particle physics, it could be realized as a Goldstone boson of a spontaneously breaking global U1 symmetry, the Petri-Queen symmetry. So okay, so this is a potential, a simplest phenomenological potential for a Petri-Queen scalar, which is a complex scalar. So it has a Mexican head shaped potential. So at a minimum of the potential, that actually this field will have a value. Field has a value, non-zero value. That's an axion decay constant. And then this axion is actually lives in the phase. Actually, is realized as an angular phase mode. That's this little dude here. So, so axion actually has been studied for a long time and has with probably thousands of papers. So the reason it's popular is that it actually has a wide range of phenomenological, cosmological, and astrophysical applications. So one of the outstanding applications of axion is the QCD axion as the leading solution to the strong CP problem in the standard model. Here's just a very crude cartoon version of the strong CP problem, which I took from Anson Hook's TASI lecture. So the neutron is made up of 3 charged particles, up quark, positively charged up quark, and 2 negatively charged down quark. Okay, so if I had no knowledge of a strong CP problem, and if I were asked to put these 3 charged balls in the neutron bag, so my first instinct is to place these 3 charges in a triangle shape. And then you could estimate, just based on EMN 101, that the electric dipole moment of the neutron. Then you'll find some estimate like that in this funny unit, okay? But experimentally, we haven't observed the neutron EDM. Instead, we have a very stringent upper bound on the neutron EDM size, which could be translated as a stringent bound on the theta angle, so the theta angle has to be tiny. So the strong CP problem is really just to explain the long observation of the neutron EDM so far, and also the smallest, or equivalently, the smallest of the theta angle. So in this QCD axion solution, this is explained by promoting the theta angle to a dynamical field, the so-called axion field. So which is named after a detergent which you could not find in the US. So when the axion when the axion field settles in its minimum of this potential, the theta angle will be dynamically relaxes to 0. So then again, at a classical level, you have these 2 negatively charged down quark placed on opposite side of the up quark. The CO2 actually configuration leads to 0 neutron EDM. Okay. In addition to a strong CP problem, axion is a classical dark matter, cold dark matter benchmark model through a misalignment mechanism. So in the early universe, the Hubble friction will hold the axion at a place in field space, like with an initial misalignment angle theta naught. When the Hubble jumps around the axion mass, the axion will actually, the Hubble friction is no longer big enough to hold the axion, so axion will actually start to roll down the potential, oscillate coherently around the bottom of its potential. And this coherent oscillation actually redshapes as cold matter. Okay. Given the QCD axion solves 2 problems at once. So it is one of the two classic dark matter benchmark models, like particle series like. The other one is WIMP. Okay. So for this talk, I'll focus on QCD axion. Of course, one could generalize to axion-like particle, and we'll hear more in the next talk. So the axion dark matter has observables at all scales, from a CMB scale, like galactic scale, and subgalactic around the stars, like the pulsars here. So really, to construct like complete picture of axion dark matter, we need an end-to-end study, and this phrase end-to-end actually steal from Kittling in talking about a different dark matter model. So the first point I want to make about axion dark matter is what I call long factorization of axion dynamics in the early universe and the late universe. By this I mean, like, what happens like during inflation to the axion actually will have a very important implications on actually the dark matter, axion dark matter distribution at galactic, subgalactic scale. So canonically, there are two types of axion cosmologies. The first is so-called pre-inflation axion. So in this case, axion decay constant is above the inflation Hubble. PQ symmetry is broken during inflation and is not restored during pre or reheating immediately after inflation. So the key feature, defining feature for pre-inflation axion is just you have additional massless degree of freedom during inflation. That's an axion. So since exponential expansion was like a stretch, like each Hubble patch with a unique initial misalignment angle. So our own Hubble patch will have like a single uniform central value of initial misalignment angle, theta 0, which is a free parameter. Since the axion is already present during inflation, it will fluctuate. And its fluctuation is independent of the primordial inflaton fluctuations. So we call it isocurvature like perturbation. So the size of this fluctuation or perturbation is set by the ratio of the Hubble, inflation Hubble, and the axion decay constant is much below 1. So this actually, so then the axion will become dark matter after inflation and reheating through the misalignment mechanism, which I just quickly reviewed. This abundance of the axion dark matter depends on this initial misalignment angle, which is not unique. So then the primordial axion isocurvature generated during inflation will tend to dark matter isocurvature. Here again, is just a cartoon version of isocurvature. So curvature perturbation is shared by different cosmic fluids, while the isocurvature is a difference between this between the perturbations of these different fluids. Okay. So this actually leads to a serious cosmological problem for pre-inflation axion dark matter. That's the so-called isocurvature problem. So basically, CMB, the Planck hasn't observed any isocurvature, and instead they have stringent constraint on the like how big the isocurvature perturbation is allowed. So the Planck data could be translated as an upper bound on the inflationary Hubble scale, assuming the pre-inflation axion dark matter makes up the entire dark matter. This the bound is about 10 to 7 GeV. So this bound could be interpreted as an incompatibility between the pre-inflation QCD axion dark matter and high-scale inflation. From the observational point of view, this means like if we observe a primordial B mode, like as predicted by the high-scale inflation, we actually rule out the minimum pre-inflation QCD axion dark matter as the dominant component of dark matter. So the other cosmic scenario for axion is the so-called post-inflation axion. So in this case, the PQ symmetry is not broken during inflation, or is restored during reheating or preheating. So the main advantage of post-inflation axion is that it doesn't have any isocurvature problem because there's no axion during inflation, or the isocurvature just wash out afterwards. Then the initial misalignment angle were like taken from a uniform distribution between -pi to pi with a set like variance. So since the PQ breaking, like that leads to axion that happens after inflation, so there will be formation of these topological defects, like axion strings and domain walls. And this decays of these topological defects contribute to the radical abundance of axion dark matter. It turned out to be a more important contribution compared to the contribution from misalignment mechanism. Actually, this is a hot topic of ongoing simulations. So these simulations are lattice simulations, like to track the evolutions of the PQ field, like during in the early universe. They assume the so-called this number, that's a number, domain 1 number to be 1. I would actually make a comment on this assumption when I make my second comment. So that here I actually list the predicted axion mass from these most recent simulations, assuming the post-inflation axion makes up the entire dark matter. So you could see this actually is roughly consistent as from my point of view as an outsider of these simulations, but they do not fully converge. Okay. And also, since PQ breaking happens after inflation, you could have all-to-one fluctuations in the field. And that will lead to formation of gravitationally bound objects, such as axion mini-cluster. So these mini-clusters are formed at matter radiation equality with a very high density set by the density at an equality time, which is much above the average dark matter density today. And later, these mini-clusters could merge hierarchically into mini-cluster halos. Again, this is a subject of ongoing simulations, what the distribution and spectrums are, and whether they will survive the tidal disruptions. Another possible gravitational bound object is so-called axion stars. These are even smaller objects with size of the axion gene scale, which is much below the mini-cluster the halo scale. Actually, in recent simulation in the early universe suggests that maybe more than 10% of these axions would directly collapses into the axion stars with the asteroid masses and the size of the Earth moon distances. And all these distributions still lead to like these distributions of these gravitational bound states. They still need more simulations to be confirmed. And also they will have big impacts on axion detections. So this is a canonical story. I just want to also make a comment based on my own research that this canonical story actually just assumes that this PQ field in which axion lives in doesn't interact with inflaton. The story could get more complicated and interesting if we like you would write down the simplest interaction you could have between this PQ field and the inflaton. So here is just a simple toy model. Actually, the new ingredient I added just these high dimensional operators in this green circle, where I add the derivative of the inflaton coupled to the PQ field, with axion as a phase. So this is a leading operator I could write down that respects the approximate shift symmetry of the inflaton, so that this operator doesn't spoil the inflaton dynamics. But it could have impact on the axion PQ dynamics. So basically, during inflation, this derivative of the inflaton at the background level will tend to inflaton speed. And inflaton speed could be much above Hubble during inflation. So in the single field inflation model, the inflaton speed is 60 Hubble. So if this, and also this operator at the background level will turn into an effective mass square term to the PQ field. So if this coefficient C is positive and this cutoff scale that suppresses high dimensional operator is not so high, and this positive contribution could balance against the negative contribution from the maximum head shape potential of the PQ field. So the consequence is that even when the axion decay constant is above Hubble, when we think canonically, just corresponds to pre-inflation axion, the PQ symmetry is broken, that due to this interaction between the PQ field and inflaton, that PQ symmetry could be restored. So this is just a cartoon picture of the mechanism. Basically, we start with the maximum head potential with PQ breaking and axion present during inflation, but due to the interaction between the PQ field and inflaton, the inflaton slow roll could uplift the potential and restore the symmetry. So I won't go into details. I just show you the consequence of it in this two-dimensional plot. So the vertical axis is axion decay constant. The horizontal axis is inflation Hubble scale. It's a BD plot. I just want to draw attention to basically two lines. So the red solid line is a conventional boundary between post-inflationary and pre-inflation axion. So below the red line is a post-inflation axion, while above the red line is a pre-inflation axion with a lot of Parameter space ruled out by the isocurvature constraint. Now with this interaction I just showed you, this conventional boundary could be pushed maximally all the way up to this green line. So this parameter space that used to be pre-inflation axion now turns into post-inflation axion with all this interesting like dynamics. And also we'll have different correlation between the B mode observation and axion cosmology and astrophysics. And even when this interaction doesn't change the classification of the axion, it could still lead to interesting new signals, cosmic and large-scale structure signals that for pre-inflation axion, even if it's just a subdominant component dark matter. So again, I will just flash through some possible signals. For instance, isocurvature spectrum, instead of being a flat spectrum as assumed, scale invariant flat spectrum as assumed in the Planck analysis, you could have these oscillatory features. Or you could have this hybrid dark matter isocurvature curvature long Gaussianity. And these modifications in the spectrum and 3-point functions actually have different shapes and scale dependencies compared to what has already been analyzed in the CMB like Planck data. So they call for different analysis and forecasts in terms of like relation to simulations, inferring these primordial long Gaussianities from long linear scales. We definitely need simulations. So the second comment I want to make is I will call it long decoupling between axion theoretical problem and axion cosmology and astrophysics. So the PQ, global PQ symmetry, is at best approximate symmetry in quantum theory and quantum gravity. This actually leads to a severe problem for the QCD axion. That's even a tiny bit explicit breaking due to quantum gravity of the PQ symmetry could completely spoil the QCD axion solution to a strong CP problem. I won't go through details, just say that in models, you could parameterize this explicit breaking by these high dimensional operators suppressed by some very high scale Planck scale. But these operators still have to be tiny, like you either has a tiny coefficient or have very high suppressed by many powers of Planck scale in order for it not to spoil the QCD axion solution to a strong CP problem. In other words, if you really want QCD axion as a solution to strong CP problem, we have to solve the axion quality problem. And this has been pointed out by a large group of particle theorists as well as cosmologists a long time ago. So a canonical solution is actually to impose additional Zn discrete symmetry, but that will lead to degenerate minimum in the axion potential. So cosmologically, that means you have these domain walls or separations between different minimum. And then the domain wall number, like quantifying the number types of domain walls, is larger than 1. So then during QCD phase transition, we'll have the formation of this stable domain wall network. This is a cosmology disaster, also known as the axion domain wall problem, because these stable domain wall networks will actually redshift slower than radiation and will quickly dominate the universe. Again, the solution to a domain wall problem, like one popular solution is just break the Zn a little bit. Again, we'll bring back the quality problem. So now we see like a kind of bad loop, like we solve the quality problem, we bring the domain wall problem, we solve the domain wall problem, we bring back the quality problem. This doesn't say like there's no solution, but it just says like you need to add many more new ingredients that will change all the dynamics in the early universe compared to what has been studied in simulations, which assume domain wall number 1. In the case of domain wall number 1 equals to 1, then the domain wall is attached to strings. Once the string network is destroyed, the domain walls will be destroyed at the same time. So that's a convenient choice for simulations. So the point I want to just make here is just there's a tension between the domain wall number equals 1, the canonical assumption for these post-inflation axion simulations, and the axion quality problem for the QCD axion, post-inflation QCD axion. So so this recent paper by these authors just weighed all the existing models, basically find that or you solve the quality problem, domain wall problem, basically the dynamics could be much richer than what has been simulated so far. You may not get a unique prediction for the axion mass, and you may have a non-conventional cosmology and astrophysics. So the take-home message is that we actually need more simulations for a wide range of post-inflation axion scenarios. So the last comment I want to make is astrophysical observables beyond flux. So at the subgalactic scale, we have a large number of astrophysical objects which serve as lateral laboratories for axion dark matter. Okay, so So I won't go through all of them. Okay, we could discuss later in discussions. So these different astrophysical objects could also be used in different ways to probe different axion couplings. So to use them, we actually usually need two types of simulations. One is the simulations for axion signals in these complicated astrophysical environments. The second one is that we lead to simulations probably for astrophysical background simulations. These are not cosmic simulations. They're simulations for like these small objects. So the point I want to make is that a lot of these signals actually depend on some flux. For example, photon fluxes, say converted from axions. So there could be more observables out there, such as polarization, pulse structure. I should say that this additional observable as polarization has been studied in literature. It's just relatively less studied compared to observable based on flux, some flux. I'll just give you an example based on my own research, so I know a little bit more about what I talk about. So this astrophysical object is J1856. It's a so-called X-ray dim isolated neutron star. So it is actually the closest neutron stars to us up to date. So what has been pointed out recently by several different groups is that there is a hard X-ray axis in the energy range from 2 to 8 keV for this J1856. So the soft X-ray spectrum of J1856 is well mirrored and well modeled by a black body emission. But the hard X-ray axis goes, you could see here, actually, this is roughly like thermal tail will just go down, keep going down. Hard X-ray axis is way above the tail, okay? So one possible explanation is like as particle theorists, we like Liu physics explanation. So one possible explanation is the axion explanation. So basically the hot dense neutron star core that generates axions with energy of keV. And then the axion convert to X-ray photons in the strong magnetic field. So this has been pointed already like a couple of years ago. So what we want to add on top of the story is that axion explanation actually has a unique prediction for the polarization of these hard X-ray photons. This is just dictated by the theory. The axion photon coupling is AFF dual, or in terms of E and B field, axion couples to E field dot B field. So the conversion of axion to photon in the external magnetic field, actually, given this operator, tells the polarization of this converted photon is always parallel to the local B field. Or in astrophysical jargon, these photons are in the O mode, the so-called ordinary mode. And these photons are 100% polarized and also energy independent and also independent of axion mass. In addition, this prediction for J1856 is robust against astrophysical complications like long dipolar structure of magnetic field or general relativity corrections. The reason that for J1856, like the conversion of axions, keV axions to photons, X-ray photons, happen far away from neutron star. The characteristic conversion scale is about 200 neutron star radius. So that's why like all these complications lead to small corrections. And in addition, another observable is that these fluxes of these hard X-ray photons actually have a high pulsation fraction. Pulse fraction just means that the maximum flux minus minimum flux divided by the sum. So for this above keV, this pulse could be as large as 50%. Again, this could be explained by axion. Yeah, sure. Sorry, I'm good. So basically, that's pretty much my last slide. So on the other hand, like the astrophysical explanation, such as we have a hotspot at the pole, is much more complicated. It depends on the surface, atmosphere, magnetosphere modelings, as well as GR corrections. So in general, we expect energy-dependent polarization and different pulse structure. But of course, for the astrophysical prediction, we need better understanding and simulations. The upshot here is that in this case, in addition to flux, we use 3D information, energy, polarization, time to distinguish between different models. So that's all I want to say. I want to repeat those 3 points and just say, we could see that simulation will play a crucial role in this end-to-end study of axion dark matter. So we need conversations and collaboration from people with different expertise, like bodybuilders, simulation experts, and data-driven observational astrophysicists, astronomers. That's all.